we start the continuation of our section about elementary sets, and let me recall that I formulated theorem about sigma additivity of volume. So it means I want to prove that if we have a representation by an elementary, that is elementary set, as well as those Mi. So if we have a representation of an elementary set as a disjoint union of elementary sets again, then the volume is equal to the sum of volumes. That is the assertion. And I defined so-called epsilon enlargement and epsilon contraction. So these are sets which one is inside, other is outside. So the volume of epsilon enlargement is equal to 1 plus epsilon times volume of the interval itself, and epsilon contraction analogously like that. So it was defined for arbitrary interval. And first step in the proof, in fact the main step, I want to prove the following property. So if we have a covering again by elementary sets, these are elementary sets, then the volume is less or equal than the sum of volumes. And of course we don't need to prove anything if the sum here is infinite. So if this series diverges, then that is infinity, hence everything is okay. We don't need to prove anything. So we can suppose this is bounded. So finite. The sum is finite. Otherwise, nothing to do. And okay, so as we know, M is disjoint union of intervals. Let's say j from 1 up to capital N p j's is joint union of intervals by definition of elementary set, of an elementary set. And every Mi can be also represented as a disjoint union j from 1 up to, let's say, n I p I j. So what we have? We have that union why does I starts from 1 not 0? Doesn't matter. What is elementary set, as I said, Elementary set. Elementary set. So, what I want to prove is that if we have union of disjoint union of intervals, these are intervals in Rn, like here in R2, just rectangles. Yeah. So, and I can forget about this disjoint, doesn't matter. So we have a union of, let's say, okay, firstly I'll write what it was. Pij, and let me denote the right hand side as union qk. So you see, I have countably many intervals. These are intervals. So these are the same intervals, but now I don't want to write down two indices. Just I plan to use one index instead of that. Okay, so then what do we do? I want to prove that the sum of volumes less or equal than the sum of volumes in the right hand side. That is the question. So if finite union of intervals is covered by countably many of intervals, then the sum in the left hand side is less or equal than the sum of these series of volumes. So for finitely many, no problem, but the question is what to do if we have infinitely many. That is the question. So it might be that finitely many qk do not cover this union. So we need just infinitely many. That is the question when we need to think about this inequality. And how we can proceed. So consider epsilon contractions of Pj's and epsilon enlargements of Qk's. So Pj minus epsilon, and for Qk I need, no, it's okay, just, yeah, Qk epsilon. Then what we have, look, so we know that union of Pj's is covered by the union of Qk's. Hence, because you see, contraction is smaller set, enlargement is larger set. Hence, for sure, smaller sets, okay, they are still disjoint, Pj minus epsilon is covered by the union of enlargements. So you see, we enlarge covering sets and contract in the set. Then, of course, this inclusion is still valid. Now, what is important? These are open sets. And these are closed, bounded, hence they're compact. Compact sets. So altogether, finite union of compact set is compact. So that is a compact set. Compact set. And it is covered by a union of open set. So hence, by the definition of compactness, definition of compact, what we can deduce? We can deduce that we can cover our compact set by finitely many. So let's say union L from 1 up to some M, I don't know, but finitely many, Q, K, L, epsilon. So you see, the union of all countably many sets covers our compact, hence we can find finite subcovering. That is by definition of compact set. So what means compact? If you have a covering by open sets, then you can choose finitely many open sets which still cover. That's very important, right? Then what we know from geometric considerations, if we have finitely many elementary sets, okay, intervals, here also intervals, then definitely sum of volumes for finitely many we can do it. Less or equal sum of volumes here. But what they are? Volume of every epsilon contraction is equal to 1 minus epsilon times volume of the set itself. So I can write here 1 minus epsilon sum of volumes of PJs. What does P minus epsilon? It's here, contraction, undefined. So the original set is that one in the middle. P epsilon is inner, P minus epsilon, sorry. P epsilon is exterior. Yeah. Okay. So that is with the left hand side, and with the right hand side analogously we can put 1 plus epsilon outside. So then we have the sum of finite sets of Q, K, L, and then of course here I can replace by the union of all by this. So what we obtained from this? We obtained the following inequality: sum j from 1 up to n pj's times 1 minus epsilon less or equal 1 plus epsilon times sum of that. Because here we have a sum of finitely many terms, and if we consider all of them, then of course it will be larger. Yeah. So we have proved this inequality for arbitrary epsilon greater than 0. And if we have it for arbitrary epsilon greater than 0, then we have that. And that's it. So theorem, oh, not theorem, sorry. First step is proved. So we have inequality in that side. Now, second step is shorter. So I want to prove that if disjoint union of MJs, MJs is a subset of M, then the sum is less or equal than M. How to prove it? It's very easy. So if we have this inclusion, then for arbitrary M natural, we have the union of finitely many MJs is in M. Oh, M was not good. M everywhere is M, very bad. Let's say M tilde number. M tilde, otherwise that is not different M. Sorry, I forget that M was used. Yeah. Okay. So for finitely many, we know from geometry that sum of volumes is less or equal than M. So we have for arbitrary M this inequality, then it gives the inequality for arbitrary. Okay? Okay. Yeah. Yeah. So you see, we have inequality in both sides, hence we have equality, which was necessary to prove. Okay, so theorem is proved. You see, that is very important property. And of course, it's natural to expect that good definition of area or volume should also extend this property. But unfortunately, that is not the case. So next section, section 4, as far as I remember, outer measure. So firstly, let me write from now on, we consider subsets of, let's say, ki equals to product j from 1 up to n minus 1/2, 1/2. That is unit cube. Better to say unit hypercube. So in dimension 3, we have this cube, like that. Not very good. Yeah. And that. Okay, that is point of intersection. Good. Point of intersection should be somewhere here. Yeah, like that. So yeah, that is cube of unit volume. So the volume of Ki is equal to 1. And it is symmetric with respect to the origin. Symmetric with respect to the origin. Okay. So and also I want to say a few words about next future. So what I plan to consider now, I want to consider simultaneously two main things. So I plan to consider Jordan measure and Lebesgue measure simultaneously. So Jordan measure is not a measure rigorously. Just a minute. Not a measure rigorously. It's just to fix somehow something. To fix something, so I need some interval of the length 1. That's it. And yeah, it's better to have symmetric interval, nothing else. But I need volume should be 1. That's important. Yeah, in fact, from 0 to 1, maybe it's the same. But for symmetry, yeah, I'm not sure. Yeah, in fact, it doesn't matter. You can consider from 0 to 1 if you want. Doesn't matter. It's not important. Just a fixed cube, better to say, of unit volume. What means measure? Measure means that we have sigma additivity property, which I wrote before for volume. So if you have countably many sets, then the measure is equal to sum of measures. Jordan measure has not this property. Nevertheless, usually in most textbooks on calculus, when multiple integrals are considered, then Jordan measure is considered. Because, why? Because Jordan measure includes area in R2, volume in R3. So these are particular cases of Jordan measure. So it means notions of area and volume which you studied in school, these are precisely particular cases of what is called Jordan measure, traditionally called. But Lebesgue measure is more general thing, and it is indeed a measure, and in fact it is used almost everywhere, I would say, in probability theory, also in functional analysis, so in most mathematical theories, you need to use Lebesgue measure. And in fact, your textbook is also uses Lebesgue measure, but only for a very particular case, Lebesgue measure 0, nothing else. So I decided to make such a an exposition of both measures simultaneously. And in fact, I'm doing here it usually in Russian also. So, but unfortunately, I don't know where it is given in English. Really, I don't know. Okay, so definition. The outer Jordan measure of a set A in Ki is equal to, so I'll denote it like that, Jordan of A is equal to, by definition, infimum of O, so A is subset Mi, sum of volumes M, sum of volumes, where infimum is taken over all coverings of A by finitely many, that's important, finitely many elementary sets. And analogously is defined Lebesgue measure, the outer. The outer Lebesgue measure of a set A in Ki is equal to mu r of A equals to infimum for all A is subset of union of infinitely many. So, oh, sorry, here. Volume, I forget about volume. Sum of volumes. Where inf is taken over all coverings of A by countably many elementary sets. So, you see that the difference seems to be not very big. For Jordan outer measure you consider covariance by finitely many elementary sets. For Lebesgue, you consider covariance by countably many. That's it. But nevertheless, it gives essentially different properties. And yeah, maybe I'll give one example which shows the difference. Example. Let A be Q intersected with our interval. It means we consider the case of n equals to 1. We are on the line. So the set of rational numbers. Then look, what is outer Jordan measure? If we want to cover all rational numbers, right, by intervals, by finitely many intervals, because what is elementary set on real 9? Is a union of finitely many intervals. So finitely many elementary sets, it means we have finitely many intervals altogether, right? So if you cover all rationals by intervals, right, then for sure you should cover the whole interval minus 1/2, right? It's impossible to cover all rational numbers without covering the whole interval by finitely many intervals, right? Is it obvious? Yeah. Hence, that is 1, because, yeah, obviously you may cover just by one interval minus 1/2. And you cannot give, you cannot get smaller quantity. But for outer Lebesgue measure, that is 0. Why? Because we can cover, so look, we consider Q as, let's say, x1, x2, so on, right? Because we know the set of rational numbers is countable, right? So it means we can numerate 1, 2, and so on, right? I mean, first, second, and so on. Countably many rationals. And then what we can do? And the union, just consider mi, let it be, let's say, xi minus epsilon over 2 power I, xi plus epsilon over 2 power I. Let it be interval like that. Or open, doesn't matter. Then what is it? You see, we have infinitely many, right? Because infinitely many intervals. And what is sum of their lengths? Volume here is length, right? And what is this? Look, here we have epsilon over sum I from 1 up to n, epsilon over 2 to the power I minus 1, right? 2 to the power I minus 1. So, yeah, okay, doesn't matter. So it means we have 2 epsilon together, right? We start from epsilon, then epsilon over 2, and so on. So altogether 2 epsilon. So you see, for arbitrary positive epsilon, we can cover our set by countably many intervals with total length, with the sum of lengths, not total length, because total length is smaller, right? Because they may intersect each other, right? But we don't care about intersections. We consider just sum of lengths. We don't care about intersections. And sum of length is 2 epsilon, so it can be made as small as we want. Hence, the outer Lebesgue measure is 0. Yeah. Once again, so what is outer Lebesgue measure of our set? Infimum of all such coverings. But as we know, we can do this number as small as we want, because we can choose epsilon arbitrarily, right? Arbitrarily small. That means the infimum is 0. That's it. Okay, so you see, big difference, right, between outer Jordan measure and outer Lebesgue measure. Okay, theorem 1 of this section, properties of outer measures. And now we'll have a break. So before I'll formulate it, so let me unify that notation by this one. So what it means, J in brackets? It means that when I write like that, then what is written is valid for both Jordan and Lebesgue. So we can accept that one and also with J. Okay, if J is in brackets, then the property is valid for both. So properties of outer measure. Yeah, we have 4 properties, and yeah, here everywhere. First, if M is an elementary set, then any outer measure, doesn't matter which, is equal to the volume. Second, if A is a subset of union of finitely many, okay, let's say Mi, where Mi elementary. Oh, no, sorry, not elementary, just AI, then Jordan measure outer less or equal than sum of Jordan outer measures of AI. Second, for any A subset here, we have everywhere we consider only subsets, but let me emphasize once more. Outer Lebesgue less or equal than outer Jordan. And we have an example where we have strict inequality. Fourth, if A is a subset of infinite union, then for Lebesgue measure we still have the same outer Lebesgue measure, same inequality. Okay, proof. Proof. Let's start with the first property. The first property. So if M is elementary set, then what happens? First of all, we can write such an inclusion. What it means? It means that we have, you see, we consider all coverings, right? So in particular, what we can deduce from this inclusion? For example, Auto-Lebesgue measure is infimum of all coverings. In particular, we can consider here such covering, just M itself, right? M itself and empty set. So like M includes M with empty set, and so on. Infinitely many empty sets. So we have countable covering of M, right? So, and outer measure is infimum. Hence, infimum outer measure of M is less or equal than this M, because volumes of empty set is 0, right? And same, of course, is for Jordan measure. So that is in one side, Now, in the second, so if, look, if A is a subset, M is a subset of a union, doesn't matter how many elementary sets, doesn't matter how many, finitely many or infinitely many, doesn't matter. Then, as we know from former section, we have the inequality for volumes, like that. And what it means, you see, every sum here is greater or equal than volume of M. Hence, the infimum of all such sums also is greater or equal than this volume. So M is less or equal than outer measure of M, maybe Jordan or Lebesgue, doesn't matter. So we have both inequalities, and it means we have equality. So outer Lebesgue or Jordan measure coincides with volume. What is it? I can see why Jordan measure in the example is equal to 1 while Lebesgue is equal to 0. For Lebesgue, I indicated that we can cover by countably many intervals with total length epsilon. And for Jordan, how you can cover all rational numbers by finitely many intervals? The only possibility is to cover the whole interval minus 1/2, 1/2. Otherwise, so if an interval contains a rational point, then two rational points, then it should contain all points between them, right? That is the point. So if there is a point in minus 1/2 which is not covered, I mean at least couple points, then the maybe for me it seems very obvious. So look, you have all rational numbers. How you may cover by finitely many intervals. So if you have finitely many intervals in minus 1/2, right? Finitely many intervals, right? And if they do not cover minus 1/2 completely, so if there are finitely many gaps between those intervals, right, then you can choose rational number in the gap, and then it is not covered by your finitely many intervals. That's it. Okay. Let me continue then. Is it okay? Yeah. So then second property. So for Jordan measure, look, so for arbitrary epsilon greater than 0, we can find, we can find a covering of our set AI. So there exists covering by elementary sets, let's say Mij elementary, such that the union, let's say AI is a subset of the union J from 1, I don't know how many, let's say Mi of Mij, and so you see the outer Jordan measure is infimum of such sums. Hence we can find the sum which is as close as we want to, so Jordan measure of AI less or equal than the sum of volumes of Mij less than this outer measure plus as small as we want, so epsilon over how many AI I have here? M. So let it be M. Epsilon over M, right? Yeah. So then what we have? Then we obtain A is a subset of the union I from 1 up to MAI. Hence, A is covered by the union of all those Mij's, right? And what we know that the sum I from 1 up to M of, so the sum of volumes of all those sets, the sum of volumes of all those sets is less or equal or strictly less, in fact, strictly less. Look, so inner sum is less or equal, strictly less, than Jordan measure of AI plus epsilon over m, and that it's just the sum I from 1 up to m of Jordan measures, outer Jordan measures of AI plus epsilon. Oops, plus epsilon. Plus epsilon. Should be here. Plus epsilon. And you see, A is covered by this union. Hence, what we obtain? It follows then outer Jordan measure of A is less or equal than, in fact, strictly less, but doesn't matter. A from 1 up to m mu j star of A I plus epsilon. So you see, we obtained almost the same inequality as we want, but with epsilon, right? But if it is valid for arbitrary epsilon greater than 0, then it is valid for all epsilon. So, second property is proved. For the third property, you see, look, we have infimums, right, in both definitions, right? But every finite covering may be considered also as a countable. Just add empty sets, right? If you have finitely many sets, you can think, okay, we have infinitely many. We add infinitely many empty sets. Then we have infinite covering, right? So it means that the set of all sums like that is a subset of this set, right? And if you are looking at the infimum of a set of numbers, right? And you know that one set is a subset of another, then infimum of larger set is less or equal than infimum of smaller set. So if B1 is in B2, then infimum B1 is less or equal infimum of B2, right? That is used. That is used here, just by this property of infimums. Okay. So for the last property, it's almost the same, but now you see for the fourth property, maybe I'll write it even just here. Yeah, just let me write like that. Fourth property, you see now I cover by infinitely many, right? Then here I have infinitely many sets. And now I'll change here a little bit, namely I'll put here 2 power I. 2 power I. Then A is a subset of infinite union. So here we have infinities everywhere. Again, infinity. Oh, sorry. Firstly, that one. That one. Not a big difference, in fact, right? So epsilon over 2 power I. And if we sum up, then we have again same. Yeah. So practically similar proof works for outer Lebesgue measure. Outer Lebesgue measure. The only thing what you need to do, you just consider everywhere infinite objects, I mean series instead of finite sums, and infinite unions. You have countably many sets once again. So that's it. Of course, I do not exclude the case when here we have infinity. In that case, of course, we don't need to do anything, right? If this sum is infinity, then we don't need to prove anything. So I can consider only finite sums, otherwise no sets. Okay. Okay. These are main properties of outer measures. Now, inner measure. And that is why I considered a fixed set. So, for arbitrary a in Ki, denote a prime to be complement to that set up to our fixed cube. And then definition. The inner Jordan or Lebesgue measure of A, which is subset of Ki, let me emphasize it once again, is equal to 1 minus, okay, let me write like that, mu star maybe j of A prime. So that is by definition. So what is inner measure? I'll put star here and maybe j up. So you see, for example, for R2, look, for R2. So we have minus 1/2, right? Our fixed cube is square now, right? And if we have a set, let's say A, yeah, let it be like that, that is A, then where is A prime? What remains, right? What remains is A prime, also that one here, right? A prime may consist of several parts, doesn't matter. And what is inner measure? It's outer measure of what remains, roughly speaking, right? So you see, better to say 1 minus outer measure of what remains. You consider outer measure of remaining part, and then take 1 minus this thing. Now, of course, in general, you should expect that the sum of, roughly speaking, if you know there is an area, then what is the sum of areas of A and A prime? 1, right? So it's natural to expect that inner measure coincides with outer measure. And that need not to be always. Okay, so main property, let be theorem 2. Theorem 2. Theorem 2. That is the only property of in the measure. For any A in Ki, in the measure is less or equal than related outer measure. Of course, here simultaneously either both are Jordan measures or both are Lebesgue measures. Don't think about other combinations. Just simultaneously either everywhere we have J or everywhere we haven't J, right? Either for Jordan measure or for outer measure. Okay, proof. Proof is relatively easy. So what we do? A is a subset of the union. I want to proceed simultaneously for both measures. That is why I don't indicate finitely many or infinitely many coverings are considered. Doesn't matter. And complement is a subset of some other elementary set. So these are elementary sets. Elementary. Then what we have? We have that union, which is just our cube, is a subset of maybe J here. Ij's, Mi, and Nj's. So you see, we have a covering of elementary set by elementary sets. Maybe infinitely many, doesn't matter. So we may apply last theorem of former section. So it follows that we have inequality for volumes. In fact, I should refer not to the theorem itself, but to the proof. Today it was given, that proof, first step of that proof. So if elementary set is covered by elementary set, then volume is less or equal to the sum of volumes. Okay, I'll write like that. So once again, let me write what is written. 1 less or equal than sum of volumes of mi's plus sum of volumes of nj's for all coverings of A and A prime correspondingly, right? But you see, outer measure is infimum of such sums, right? And if we have this inequality for all coverings, then it follows same inequality is true for infimums. So I can write here A prime. And that is precisely what I want to prove. Because, look, if I put this to the left-hand side, that is precisely the definition, right? 1 minus outer measure of complement is equal to inner measure of the complement. Okay. So you see that inner measure, as it should be expected, right, is always less or equal than outer measure. So this was rather short section, and now essentially longer section, which I hope to continue in next weeks, because now nobody knows about next week's. But I hope I'll be able to do it here once again, maybe just through the Zoom, I don't know. Let's hope for the best. So now I can give the main definition, and okay, maybe I should reserve one blackboard in dry. I think, yeah, I have only 10 minutes, so don't need to erase everything. So, yeah. They're shared, but in Russian, unfortunately. I have to translate them. I'm sorry. I have to translate them. I hope to do it in next future. Yeah. Oops. Just on the side of Department of Higher Mathematics, you can find it easily. In Russian, sorry. And also main sources are in Russian. There is one book in English, but for Lebesgue integrals it's good, same same construction which I use usually for Lebesgue integrals, for multiple integrals, but unfortunately for Lebesgue measure it's different. So now makes no sense to recommend it. But for multiple integrals, maybe I'll do it. Okay, so for next semester. Now section 5, just measure, right? Or maybe I forget. Section 3, how I called it, measure or elementary sets? I hope not. Elementary sets, okay, very good, yeah. I was afraid that I made such a measure, such a title. Okay, definition. A, which is in Ki, is called Jordan and correspondingly Lebesgue measurable if corresponding inner measure coincides with corresponding outer measure. And you see example 1, which shows once again same set which we considered before. That is not Jordan measurable. Why? Because as we know, so Jordan outer measure is 1, Lebesgue outer measure is 0, right? What is about inner? Of course, inner measure, inner Lebesgue measure, what is inner Lebesgue measure? Look, every Lebesgue measure, every measure, inner measure, is always non-negative, right? Because 1 minus, and the set is in the fixed cube of volume 1, right? So it's non-negative, right? And it is less or equal than outer measure, as we know. Outer measure is 0, hence inner is also 0, right? So it means that this set A, oh, I forget to say that is A is Lebesgue measurable, right? Lebesgue measurable. And, oh, I forget to make a notation, and that is precisely mu, maybe J of A. So if they coincide, then their common value is called Jordan or Lebesgue measure correspondingly, right? So you see, this set is Lebesgue measurable, but what is about Jordan? So outer Jordan measure is 1. Now what is complement? A prime. That is minus 1 half 1 half minus q. So irrational numbers, right? Of course, outer measure, Jordan measure of A prime is also 0, right? Oh, sorry, is also 1. Is also 1. Is also 1. Because if we want to cover all irrational numbers by intervals, for sure we need to cover the whole interval, right? Same consideration. Hence, inner Jordan measure of A equals to 1 minus outer measure of A prime, that is 0, right? So you see, inner measure is 0, outer measure is 1. So the set is not Jordan measurable, right? But for Lebesgue, you see, that is not the case. And in fact, there are non-measurable sets, but I mean, Lebesgue non-measurable sets. But construction uses so-called choice axiom. That is an axiom from set theory, and in fact, non-measurable Lebesgue non-measurable sets, they never appear when you consider some natural questions. I mean, but they exist, non-measurable sets, unfortunately. I mean, Lebesgue non-measurable sets. For Jordan, you see just a simple example. And maybe I'll make a couple remarks. First, every elementary set is Jordan and Lebesgue measurable with measure of m equals to volume. So for elementary sets, nothing new. Both Jordan and Lebesgue measure, they give the same. And second remark, every Jordan measurable set is Lebesgue measurable. Why? That is true because, remember the inequality. There was such an inequality. For Jordan and Lebesgue measure, right? Then automatically we have similar inequality for complements, right? And if I multiply from 1, it gives opposite inequality. And these are precisely in the measure. So you see that for arbitrary set we have such chain of inequalities. And it gives what we want. So you see. Sorry, I think, yeah, of course, I mixed here. I'm sorry. So everything should be different. Yeah. I mixed where to put J. Yeah, sorry, like that. Yeah, then it's okay. Now it's okay. Yeah, now it's okay. Yeah, so you see, if our set is Jordan measurable, so left and right hand sides coincide, then those coincide as well, right? And it means that's it. So if you have Jordan measurable, then it's automatically Lebesgue measurable, and Lebesgue and Jordan measures coincide. Okay, that's all for today. Thanks.